8.6, we've made it to the end of chapter 8, in which we were diving in and exploring quadratic functions. So we started off this chapter actually discussing the differences between linear, exponential, and quadratic, and explaining that we were going to spend some time really getting to know the quadratic functions, learning how to graph it from all of its key properties. And so hopefully by now, at this point in the chapter, you have a good idea and understanding of what a quadratic function looks like. Well, we want to compare it today to the linear function and exponential function and talk about average rates of change. So our first example asks us to use your technology to plot the points, tell whether the points appear to be linear, exponential, or quadratic, just based off of the shape. So if you haven't graphed these, take a second to pause the video and plot these points and then resume your video. All right, hopefully you've got those plotted. In A here, we've got the points 8, 4, 4, 0, 0, -4, -2, -6, and -4, 8. Those were our purple points, or our navy points, that were graphed here. And we can see that that fits into a linear model. So that's a linear representation of that data. In B, we graphed -3, 6, -2, 1, 0, -3, 2, 1, and 3, 6. You'll notice there's a little bit of symmetry with those points there. And those are our green points. And those green points formed a parabola, and we know parabolas represent quadratic functions. All right, finally for letter C, we graphed the point -3, 9, -2, 5, -1, 3, 0, 2, and 1.15. We can see that that's decreasing at a pretty steep rate and then tapering off, and that's going to be that exponential decay, or in other words, just an exponential function. So being able to graph your data, whether you're using technology or just graphing it by hand, and taking a look at the shape of that data, the trend of what's happening there, will lead us to what type of function we're looking at. All right, going over to page 2, we've got another way to determine, based on the data, what model is best to represent that data. So take a second to read through this here. This is called the differences and ratios of functions. You can look for patterns between consecutive data points to determine which type of function models that data. The difference of consecutive y values are called the first differences. The differences of consecutive first differences are called the second differences. Now, here's the point. If we have a linear function, then our first differences will be the same. They will be constant. It will be a linear function. If the second differences are constant, then it will be a second degree polynomial. It will be a quadratic function. If there are consecutive y values that have a common ratio, not differences now, but a common ratio, then that function will be exponential. So let's take a look at an example here and show you what we're talking about. Tell whether each table of values represents a linear, exponential, or quadratic function. So let's zoom in on our table for letter A. We have our x values of -2, -1, 0, 1, 2, and then our y values of 11, 5, 3, 5, 11. So you might already start to say to yourself, I recognize a little pattern there. However, we're going to show you how to use these first differences. When we take the first differences and our y values, we always start at our further out to the right, and we take our differences going right to left. So here's how this works. We say to ourselves, what is 11 minus 5? Well, the difference between 11 and 5 is positive 6. Next, we're going to do the same thing, moving right to left. What is the difference between 5 and 3? That's 2. What is the difference between 3 and 5? Well, that's -2. And what is the difference between 5 and 11? That's -6. So you can see here that our first differences are not constant. Let's try taking our second difference. All right, so our second difference, we're once again going to start out here to the right and go moving to the left. We'll say 6 minus 2. What is 6 minus 2? That's 4. What is 2 minus a -2? That's also 4. And finally, what is -2 minus a -6? that once again is 4. So you can see here that our second differences are constant. And when we have a second difference that are constant, we know that this is a quadratic function. So this data models a quadratic function, and it would form a parabola. All right, let's look at example B now. We have our table of values, and we can see our y values go from 6 to 8 to 10 to 12 to 14. That might be tipping us off here as to what type of function it is, but let's go ahead and do our first differences. So starting out here at 14 and moving to the left, we say 14 minus 12, that's 2. 12 minus 10 is also 2. 10 minus 8 is 2. And 8 minus 6 is 2. Well, we found that our first differences are constant. And when our first differences are constant, we know that this is a linear function. So we're going to say that graph B, the data there in graph B represents a linear function. All right, our last example here is letter C. And we can see that our y values go from 0.5 to 3 to 18 to 108 to 648. They're jumping up by quite a bit. I'm going to test and see if there is a common ratio. So a common ratio, remember, can be found by taking the second term and dividing by the first term. 3 divided by 0.5 is equal to 6. Now, see if that is a common ratio between all terms. Going from 3 to 18 is being a multiple of 6. 18 times 6 would give me 108. And then 108 times 6 is also 648. All right, so our common ratio here is equal to 6. And when we have a common ratio between our y values, we know that this must be an exponential function. So letter C, our data represents an exponential. All right. Jumping down here to our last little thing here for our notes for chapter 8, we're going to talk about the average rate of change. The average, see if I can spell that right, average rate of change. Now remember, rate of change is just slope. The average rate of change is for a function, f of x, that goes between 2 points where x is a and x is b, and it's simply the slope of the line through those sets of points, a comma f of a and b comma f of b. So another way to think about that is just f of b minus f of a divided by b minus a. And that's really just your change in y value over your change in x value. It's the same slope formula that we've been using all year long. All right, let's do an example with that. It says 2 news websites open their membership to the public. We want to compare the website memberships by calculating and interpreting the average rates of change from day 10 to day 20. All right, let's start off by looking at the graph here for website A. On day 10, it looks like our membership here is right below 800. So let's just estimate that at 780. So on day 10, we had 780 members. Well, let's go out to day 20 now. Day 20, it looks like our data tells us that we have about 1,600. So day 20, 1,600 members. If we want to find the average rate of change, we are simply doing the change in y over the change in x. So we're going to take 1,600, subtract 780, and divide that by 20 minus 10. That's going to result in 820 over 10. Now, when we divide off that 10, we're going to end up with 82. Now, what does that mean, 82? Well, that is 82 new members per day that are joining website A. All right, let's look at website B now. And website B is laid out in a table of values for us. And remember, we're going to go from the average rate of change of day 10 to day 20. So here's our 2 data points. We'll write them out as coordinates, as ordered pairs. And now we'll do our average rate of change, which is simply calculating the change in the y over the change in x. So 1900 minus 1200 divided by 20 minus 10. That's going to result in 700 over 10, which is 70 members per day. And that's it. We'll see you tomorrow in class.